In this video, we will see what are the types of isolated singular points. Now, this is how it is classified: removable singular point, pole, and essential singular point. Okay. Now, let us see what is a removable singular point before we move on to the rest. Removable singular point. Now, how do we define this removable singular point? Okay. Now, it goes like this. If a single valued function, you must note certain things, it's a single valued function. Okay. If a single valued function is not defined, okay, it is not defined at z equal to z naught. And moreover, if the limit z tending to z naught, f of z exists finitely, then we will say z equal to z naught, that is z naught is a isolated removable singular point. So there are two cases here. I told you first, the function should not be defined. That's what we have seen in singular points, is it not? The function should not be defined at z equal to z naught, provided the limit z tending to z naught f of z should exist finitely. Let's just go with an example. Let us go with this example. F of z is equal to sine z by z. Now, mathematically proving this, there are two ways of identifying what is the whether the singular point is a removable singular point or not. First of all, z equal to 0 is the isolated singular point here. Z equal to 0 is the isolated singular point. Now, we will have to check whether z equal to 0 is a removable singular point or not. There are two ways of checking this. Now, according to this definition, what can we do? We can just check whether limit z tending to 0 sine z by z exists or not. It does exist. Here, limit z tending to 0 sine z by z is 1. We can just prove it later. Okay. So, limit z tending to z 0 sine z by z is equal to 1, which means the limit exists finitely. Therefore, z equal to 0 will become a removable singular point. Okay. Now, there's also another way of proving this using Lorentz series, which you should have read earlier. Using Lorentz series also we can prove this. Now, how can we represent sine z by z? Now, you know that sine z can be written as z minus z cube by 3 factorial plus z power 5 by 5 factorial, and it goes on. So, sine z by z would be 1 minus z square by 3 factorial plus z power 4 by 5 factorial, and it goes on. Now, when you look at this series, this f of z, when you look at this, you can see that there are no negative powers of z. There are no negative powers of z. Okay. There are no negative powers of z in this given function. Now, in Lorentz series, I think you would have studied that earlier. You will have the principal part and the analytic part. Principal part is where you will have negative powers of z. Now, in this given function, there are no negative powers of z. Therefore, z equal to 0 is said to be a removable singular point. This is another way of checking whether the isolated singular point is a removable singular point or not. Now, this is the solving part of the question. Now, for a better understanding, what can we do? We can just see how this is happening and why is it called a removable singular point. In this video, we will see. Okay, now consider this table. We have z and the functional values of sine z by z. Now, I've given values of z here and the functional values of sine z by z. And we also know that limit z tending to 0 sine z by z is equal to 1. In other words, as z gets closer to 0, the functional value gets closer and closer to 1. It can also be visualized in the following graph. Just look at this graph. You can see that as z gets closer to 0 from either sides, the functional value approaches 1, and which can be identified as a gap here. Okay, there's a hole here in the graph. This is the point at z equal to 0. Okay, at z equal to 0, there is a hole here because the function is not defined here. Okay. Therefore, what do? We just redefine the function saying f of 0 is equal to 1. Okay. When I redefine the function as f of 0 equal to 1, this hole will disappear and therefore the graph becomes complete and it is analytic at z equal to 0. Which means what? Z equal to 0 is no more a isolated singular point. Okay, which means, in other words, this isolated singular point can be removed from there by redefining the function f of z at z equal to 0. Therefore, that is why the name says that this is a removable singular point. We will see a few more examples on this. Let us consider the next example. That is f of z is equal to 1 minus cos z by z square. Here, the isolated singular point is z is equal to 0. Now, we must check whether this isolated singular point is a removable singular point or not. So, first we will check whether the limit z tending to 0, f of z, that is 1 minus cos z by z square, exists or not. Here, the limit does exist. It is 1 by 2. You can just check it. Okay. So the limit exists and therefore z equal to 0 is a removable singular point. Okay. Now, the other way of proving this or checking whether the isolated singular point is a removable singular point or not is through Lorentz series. Now let us go to that. So how do we do it? 1 minus cos z by z is the given function. Now we know that cos z is nothing but 1 minus z squared by 2 factorial plus z power 4 by 4 factorial and it goes on. So when I say 1 minus cos z by z square, the series should be 1 by 2 minus z square by 4 plus z power 4 by 6 factorial and it goes on. Okay, so this is how the series is. And you can see that there are no negative powers of z observed here. There are no negative powers of z. Therefore, I can say that z equal to 0 is a removable singular point. Okay. Z equal to 0 is a removable singular point. So this was easier to check. Okay, there are two ways of checking, through the limit and through the Lorentz series. So now, in case if you are going to redefine this function, what do? We will just redefine f of 0 as 1 by 2 so that this isolated singular point can be removed. Okay, we can just use the graph to visualize it. Look at this graph. This is the graph for 1 minus cos z by z square. You can see that the removable singular point exists at z equal to 0. You can see the small hole here. So there is a gap. So you know that limit z tending to 0, f of z is equal to 1 by 2. So from both the, so as z tends to 0 from both ends, the functional value approaches 1 by 2. So what do? When I redefine f of 0 as 1 by 2, this gap will be filled and therefore z equal to 0 will become a removable singular point. Okay. So next example, let f of z is equal to tan z. Okay, we have discussed this earlier. Tan z is nothing but sine z by cos z. Okay, and the isolated singular points of this function f of z is equal to tan z is nothing but z is equal to pi by 2 plus n pi. Okay. And taking the values 0 plus or minus 1 plus or minus 2, and it goes on. Now you can see here that we will have to check whether these isolated singular points are removable singular points or not. So for that we will just check the limit as we have done it earlier. Z tends to n pi plus pi by 2 operating on f of z. So that will here the limit will not exist. Limit does not exist. You can just check this out. The limit will not exist. Therefore, we can just conclude that z equal to pi by 2 plus n pi will not be a removable singular point. So this is just another example where you can show that the isolated singular point is not a removable singular point. You can also just see that using a graph where you can just check this graph of tan z showing the limit at z is equal to pi by 2, that it does not exist finitely. This graph is for z is equal to pi by 2. Similarly, you can check for the other values, the other isolated singular points, 3 pi by 2, 5 pi by 2, and so on. You can see the red lines and the green line. Both the curves are approaching infinity from both ends. And at z equal to pi by 2, you can see the vertical line going to infinity on both ends. So there is no hole on this vertical line. So letting us know that these isolated singular points are not removable singular points. Thank you.
These are the questions you can try. Check whether they are removable isolated singular points or not.